and I can compare temporal and spatial. Temporal is time indexed. Spatial, you've got to drop those breadcrumb states. Temporal reduces complexity for your state diagrams, your call diagrams, and your models. On the spatial side, it increases complexity in the state diagrams, the call diagrams, and the models. Temporal reduces code size, increases reuse, inherently has trace, and it's preemptible. On the spatial side, codes get big and unwieldy. It decreases reuse. Trace is manual. You have to insert statements, and it's marginally not preemptible. I've created a temporal state machine that consists of 3 parts: the engine, the table, and the procedures. The engine is indexed in time. The engine consists of a preemptible while loop, a test condition, whose result is either true or false. True or false. Both results have their respective behaviors: next rule or step and trace. The logic in the table in each row corresponds to 1 increment in the time index. Each column corresponds to an element of the code in engine. These arrows show the relationship between the engine and the table. The procedures just manipulate data. They may contain loops or instantiations of subordinate engines. Let me define coherent. Each row does or handles 1 state and does it very well. The implementation. The interface to the engine may change, excuse me, but the fundamental core remains the same for each engine table type. You can see the dynamic state is coming into this engine. The engine is, while preemption loop is turned to true, so while the local and global engine values are true, this will iterate. The dynamic state is compared to the static state at this location, at this row in the table. If it's true, it dynamically binds to the true, provides a trace, returns the next location to execute to. If it's false, it dynamically binds to the false and provides trace, and then finds the next location to execute to. In Delphi, the elements of the structure are defined as such. I create a procedure type, procedure of object. I create a class called TCOSA rules. It contains the rule name and step location. It contains the static state definition. This is where the logic test is. The procedure that will be dynamically bound to in the engine. The next location that it will transition to. It contains the dynamic binding false procedure, and the next location that it will transition to, and an integer. There are other structures I don't have time to go through. For example, you can change the logic test over to be defined as a Boolean function, and rather than testing for an integer here, you can test for return on the Boolean function. The allocation for the logic table and the procedure prototype definition for filling in the logic table. Again, the array consists of TCOSA rules. The prototype is to fill in the logic array. The implementation logic, this routine fills in the array. It creates a row of TCOSA rules. It fills in the time, the state, the true and false, the next, the trace. When the application initializes, these are dynamic calls to the routine PBRT. So these must be, in Delphi, this table must be set up before the engine can be used. In C and C++, this happens statically at application load time. Consider that through a private interface, if I want to change my logic, all I need to do is change the parameters in a call to PBRT. With the right rule step location and the change to any of the other parameters, I can change the logic or the data manipulation of the program. This table replaces 112 spatial logic tests. Yes, it's small and compact, but you can download this presentation and take a closer look. For those of you not familiar with Delphi, the curly braces are treated as local comments. I use 0 and 1 to indicate what state the engine is in after each behavior. For example, dynamic state is negate, That means that this would be true. That means that the first operand is going to have a negative sign in front of it. Then there's a call to negate, and after that the engine is turned off. If the first entry is a number and not a negate, then it's going to go through and clear the buffer. The engine is going to continue to run. It's going to transition to oper +1, and here at oper +1, it's looking for a digit. If it finds a digit, it says, yep, any number, begins to build the integer portion of the string, comes back and says, yep, I'm going to turn the engine off, and goes back to the message loop or whatever the event, excuse me, the interrupter event that caused the transition. The calculator provides a typical 1,000+ lines of code example. The user of the calculator has a natural temporal perspective on how the device works, actually how it's used. Think about how the user enters a problem. They put in an optional sign, enter the first operand, then they do the operation, add, subtract, multiply, divide. Then they put in an optional sign, second operand, and select a result, add or equals %, or a chain operation where they're going to iterate back on the operation and continue to enter in a value. The user's perspective is generally temporal. Let's look at entering -pi followed by a subtraction operation. This next series of slides show an animation entering in the first operand up to the operator. So here's the time pointer. Entered in, shows up in the actual application. And this is a little model, and it shows the 3 being entered in. The temper has transition. The dot has been entered. The 1 has been entered. It's going to iterate here now and let the 4, 1, 5, 9 come in. And then the operator has been entered. It's not a number. It's not a clear entry. It's not addition. It's a subtraction. It's going to transition the subtraction or the operator into the next. So now, understanding time. This is temporal logic. -pi was entered, and then the subtraction operation. And on a larger scale, you can see that -3.14159, these are the values that are entered into here. With temporal, I know where I am, I know where I came from, and I know where I'm going. Quantification. I'm going to compare the exact same functionality between temporal and spatial. Temporal uses 10 states to enter in the 9 elements, -pi, subtract. This is 90% efficient. The spatial, notice there are several counters are missing in order to fit this on one slide. Spatial logic creates significantly more trace. Notice that the ITE, the spatial, starts at time 19. There were 18 states getting ready to start. The efficiency of this code is 9 elements divided by 54 states, or 16.6%. This means 45 tests were made as overhead, or about 83% of the programming effort is costly overhead that must be maintained. Anyone not believing me, please take the challenge.